Okay, so we're going to next get into simple circular motion. So things that move in a circle continuously. So here's an example. I don't know if you remember or not this toy. It's called the Skip It. I used to have one when I was a kid. It might be before your time a little bit. But basically you take the toy and you put it on your foot and you spin it around in a circle with your foot and you jump over it every time it goes in a circle, and it counts how many times it spins around. So the tension in the string is the centripetal force that keeps the object moving in a circle. So here's a diagram of what's going on. The object at any given point, for example right here, it has a velocity that's pointed tangent to the circle. So it's moving this way. So for example, if we were to cut the cord or the string or whatever's spinning the object and just let it go freely, it's going to continue moving in the direction that it had the velocity at that moment. So over here, it has a velocity pointed down. Down at the bottom of its path, it has a velocity pointed to the right. Over here, it has velocity pointed up, and this is all relative to this figure. But the force that's keeping it moving in the circle is always pointed towards the center of the circle. And in this case, that centripetal force is due to tension. So the object is accelerating. Even if it does have a constant speed, since its direction is constantly changing, it must be accelerating. We know that acceleration is a vector and it has both magnitude and direction. So even if the magnitude is staying constant and the direction is changing, that means that it is accelerating. So acceleration is also centripetal, which means that it is center seeking. So the direction of the acceleration is also pointed towards the center, just like the force. And we denote it with an A subscript C. So every time you see this force vector, there's also an acceleration. And we know this because the net force is in the same direction as the acceleration, and vice versa. So the object with circular motion is accelerating. Therefore there must be a net force on it. Since acceleration is towards the center of the circle, so is the direction of the net force, which we call centripetal force. Centripetal force, it's the force towards the center that maintains the circular motion. It is always described by another true force. So we can't just say, oh, it's due to the centripetal force. There's always a cause, so forces that we've gone over. For example, when we were talking about the Skip It, it was tension. So what are some other examples of true forces? So this ride at an amusement park, if the people are sitting in swings and they're moving around, the swings are being held by some cable, then the force that's keeping them moving in a circle is the centripetal force due to tension. Right here we have the moon orbits around Earth, so the force that's keeping the moon in this circular motion is a centripetal force known as gravity, the gravitational force. And then here you can see these two guys are riding on motorcycles. The walls are actually vertical, so they're going fast enough to overcome gravity. They're still experiencing the force due to gravity, but that's not the force that's keeping them moving in the circle. The force that's keeping them moving in the circle is the friction that exists between the wall and their tires, which provides a huge normal force. So the normal force is what's keeping them moving in a circle. Of course, there's an equation to go along with it. The centripetal acceleration equation is velocity squared divided by radius. To look at a little bit of unit analysis, it's v squared over r. So we go ahead and plug in our units, meters per second squared. There should be another meters squared up in the numerator, Let's add that in there. Meters squared divided by seconds squared. So one of our meters cancels, leaving us with meters per second squared, which is our unit for acceleration.